Okay, good morning, everyone.
Good morning.
Get out and brave the cold this morning. Give everybody a chance to light in a spot today. Once again, we're working in a series of Does God Exist? It's presented by Dr. Stephen Meyer. In last week's episode, he took a closer look at what happens inside of a living cell, and we kind of learned that amino acids that are arranged in a specific order create proteins, and those proteins perform specific functions in a living cell, and there's all kinds of those things working in each cell in our body, and we have trillions of these cells in our body. So pretty remarkable thing. And he relayed to us that amino acids are a lot like an alphabet of letters. That when you arrange them in a specific order, you get, in an alphabet, you would get a word. But if you do amino acids, you get a function if you arrange them very specifically. And he started to explain what the odds were of that just happening on its own. And he continues that exploration today, and there's going to be some math in this one that I'm just going to tell you, it's above my ability to calculate, but you'll get the idea of just how really how strong the odds are against just a simple natural occurrence, and that the deeper you look, the more evidence there is here to say that not only is there someone who created this, but there is purpose and design behind what was created that brings each of us to a living being. So we'll talk a little bit more about this when the lesson is over. But in the meantime, soak up as much as you can, and then we'll take questions afterwards. Go ahead, Debbie. Oh, I do have one other thing. So, before we go, I want to go to Psalms 139, verse 11. I meant to say this before, and read it to you. And I want you to think about this while we're watching through this little episode. Good old David would pen some awful nice words in the book of Psalms. But he would pen this in Psalms 139 in verse 11. He says, "For you formed my inward parts, you covered me in my mother's womb. I will praise you, for I am fearfully and wonderfully made. Marvelous are your works, and that my soul knows this very well." And David, of course, would have probably the greatest grasp on who he was and the greatest grasp on who God was, more so than most men. So I find a lot of remarkability in these words. But we'll go ahead and get started. Debbie?
Last time we were talking about what I think is just an absolutely phenomenal discovery. If you just step back and think about it. We're all so used to hearing about DNA. It's the double helix. You see it out there. We know that we solve criminal cases because of the DNA evidence. So we're real familiar with DNA. And we see the double helix icon all the time, and we think, well, that's pretty neat. But how many of us stop and think about the fact that the DNA molecule encodes information, that it's got digital code along the spine? I was talking to my doctor the other day. She was asking, well, what are you going to do this class about? And I started to tell her about the book that I've written about DNA, and she said, yeah, DNA does have digital code. And we get inured to it, we get used to it, and we kind of forget that all of life, the function of life, depends upon a form of technology that we're using in our high-tech computer domain. Bill Gates says DNA is like a software program, only much more complex than any we've ever devised. So as we begin to think about the question of the origin of life, and as we realize that to build a new cell, to build life in the first place, you've got to have code, it raises a really exciting question. Where did that information come from? In this lesson, we're going to focus on the ideas that scientists have had who are operating out of a completely materialistic or naturalistic framework. They're not typically ideas that would be seen to support the existence of God. In fact, they're proposed mainly by scientists who have a view of science that supports a completely materialistic worldview. So let's see how well those explanations have played out. How well have they been able to account for the digital code that's in DNA? So let's dive in. Last time we were looking, this time we're going to look at the competing explanations, especially those that are coming from the standpoint of people operating within what is understood to be the mainstream scientific approach. But according to Jacques Monod, if you're a scientist, you want to explain something, you've got two basic tools. You can invoke chance variations, and you can invoke principles of what he called necessity. And by that he just means something like a law of nature. If I drop a tennis ball and it falls, we're going to say, well, it does that because of gravity. And if it does that repeatedly, we're going to say it does that by the law of gravity, and the law of gravity produces a certain effect of necessity. It has to happen that way. It's just the way nature's put together. So that's the strategy that scientists want to use when they're explaining things. And let's see how well those strategies have played out in the attempt to explain the origin of this mysterious information that's encoded in the DNA molecule. First approach. Let's try this chance idea. Well, first of all, there are many scientists that have thought that chance has played a role. One scientist, Albert Leninger, was the author of a very popular biochemistry textbook that sold hundreds of thousands of copies. And in his section in the book on the origin of life, he puts forward this basic idea that even though life is really complex and improbable, it eventually arose by chance alone. And he says, we now come to the critical moment in evolution in which the first semblance of life appeared through the chance association of a number of abiotically formed macromolecular components, a lot of syllables. What he's just saying, we're talking about the amino acids. They arrange themselves into proteins by chance alone, by chance variations. So let's try a chance idea here. If I were to, for example, hand out a Scrabble letter or two, and you guys were to oblige me in a little demonstration, would you mind just going up to the board on the right and writing down whatever letter you got out of the bag, and let's see if we can, by chance alone, pure dumb luck, come up with some specified information. Remember, that's the kind of information we want to explain. So would you mind walking to the board and writing what you got a blank? Well, all right, I'll let you choose another one then. Everybody's a comedian, huh? Okay, very good. Julio, you want to have a go there too? There we go. Go. And we'll just keep going for a bit until we get some nice specified information appearing on the board. Morgan, you want to have a shot? How are we doing? What do we got? CY. Okay, we got some promise here. Very good. Okay, don't put any of them back. We've got to make this totally random. Okay, you want to go? All right, what do we got? Do we have some specified information yet? Hey, that's pretty good. Okay, what's that spell? What's that spell? Okay, you guys had me worried there for a minute, right? Because CYNAL, it's almost canal. That is, in all the years I've done this demonstration, that's the closest I've come to somebody getting a real word in a few short letters. Sometimes this happens, though. You get a few letters at the beginning that form something that's almost word-like, but I always win the point. I always win the point of the demonstration. How do I do that? I let you keep choosing letters, right? Because I know about the odds, and eventually the gibberish is going to completely swamp any meaningful sequence, all right? So that's the first lesson. If you want to produce specified information, chance alone is not a very effective mechanism. The second lesson, I think, has to do with why this is so difficult. And it has to do with something called the problem of combinatorials. I have a way of explaining this that does not require anyone to be a math major. Have you ever seen these little puzzles? You've got 4 dials, and you've got different body parts of dinosaurs here. And the idea is you're supposed to go by like this and try to get the head of the Tyrannosaurus to go into the body with the Tyrannosaurus and the part that labels him a Tyrannosaurus. And it's actually kind of difficult because you've got 1, 2, 3, 4, 5, 6 possibilities on each dial, and then you've got 6 times 6 combinations in 2 dials, right? If you think of all the different ways of combining these sides with these sides, it's 6 times 6, not 6 plus 6, right? So how many is that? How many combinations are there with just the first 2 dials? 36, right? And then if you multiply by 6 again, what do you get? 6 to the third. Oh, you are a cheater. Okay. Well, I know it's 216, I think. Is that right? Okay, and then I think the next is then times 6 again, I think is 1296. I think I worked this out one time. It doesn't really matter what the actual numbers are, though, despite my insult. Okay, sorry. It's really, you get the idea. It's the number of possibilities are growing exponentially, not additively. Do you see the problem? Okay, now this is a big problem in any linguistic system because the number of possibilities explode. Let's go back to our example over here. 8 spaces, eight slots. How many combinations of English letters are possible in those 8 spaces? 26 to the 8th power, okay? But that is a whopping big number of possibilities. And it turns out in any linguistic system, the functional possibilities are a very small, minute fraction of all the total possibilities, all right? Now, it also turns out that that's what's going on in DNA and protein, and it's one of the reasons why explaining things by chance is so very difficult. Another illustration. Combination lock, a bike lock. Most of these they have 4 dials, right? And each one has 10 possibilities. So if you've got 4 dials, 10 digits, you've got 10 to the 4 possibilities, or 10,000 possible combinations. So if I did the little illustration we did before and passed this around, what do you think the odds are of someone actually getting it on the first try? Well, exactly 1 in 10,000. Not very good, right? But now just imagine I had a hypothetical bike lock with 10 digits, okay? Now we don't have 10 to the 4 possibilities. We've got 10 to the 10, which is 10 billion possibilities, right? So that's an enormously much bigger number just by adding 6 more dials, all right? 1 in 10 billion. Now let's think about proteins. Okay, we've been talking about how the amino acids are the building blocks of the proteins, right? At each one of these sites, how many possible amino acids could be part of a growing protein? Do you know this from the biology? That there are 20 possible protein-forming amino acids. Okay, so you've got a 1 in 20 chance at each site. So to get at 2 sites, how many possible combinations do you have? 20 times 20 again, so 400. If then you go to 3 sites, how many possible combinations? 20 times 20, the 400 times 20 again, 8,000. Very good and quick. Okay. Now 8,000 times 20 again, 160,000, and we're only to 4. Okay. So there's a vast number of possibilities. You've got a 1 in 20 times 1 in 20 times 1 in 20 times 1 in 20. Going out however many sites you have for amino acids. So in a chain of amino acids that's just 10 sites long, you're already to 20 to the 10 possible combinations. That's 10 trillion possibilities. But most proteins, even modestly, shortest proteins, are 100 to 150 amino acids. The average length proteins may be 300 to 400 amino acids. So can you see what's going to happen to these exponential numbers as far as the number of possible ways of combining the amino acids? Let's take a protein of 150 amino acids in length. That's a very modest, not real big one, okay? So we'll do that same calculation. We've got 150 sites with 20 possibilities at each site, 20 to the what power? 150th power. Convert that to base 10, that's 10 to the 195th power. We can't even begin to grasp how many combinations that is. Do you know there's only 10 to the 80th elementary particles, protons, neutrons, electrons, in the whole observable universe? You're getting some idea of the scope of these numbers. Now, we know that not every single amino acid combination is functional, but we also know that many of them are. So there's a big question if you're just kind of trying to assess how likely is it that we'd find a protein by chance with all the amino acids in that prebiotic soup interacting with each other for, say, billions of years. And I give it a lot of time. How likely is it that we'd ever get a protein to arise by chance? Well, imagine you're looking for red marbles in a jar of blue marbles. Well, to know the odds of finding a red marble, you want to know something about the ratio. Is it 1 out of 1,000, or is it 500 out of 1,000? Makes a difference, doesn't it? So I have a colleague who's been interested in the whole question of whether or not life could arise by chance for a long time. His name is Doug Axe. He's a molecular biologist. He did his PhD at Caltech. He worked for 14 years at Cambridge University, and he wanted to find out how common or how rare are the functional sequences of amino acids among the big space of all the possible amino acids there are. And he chose to work on a protein of about 150 amino acids to start to get an answer to this question. Now, what he did is he found that there were indeed many combinations that produced functional proteins. But he also found out that the ratio was very, very small. Essentially what he was asking was this: for protein that forms a function, how many combinations of amino acids are there? You kind of get the idea? He's trying to get that marbles to marbles ratio. You know, this is like the red marbles we want and the blue ones that we don't, okay? And he came up with a really amazing number. And it's 10 to the 74th power. Now that seems a little less scary because we just looked at this great big number, but this is still an enormously small probability. In other words, if you think of all the amino acids that there could be as a big haystack, and you start searching around for the functional ones, the ratio of functional ones to non-functional ones is like 1 to 10 to the 74. That's the ratio. So finding a functional protein by chance, just on this calculation, you can see is going to be easy or hard? Pretty hard. So then we're going to start putting up some numbers on the board. So just to get the amino acid sequence properly, you've got an odds of about 1 in 10 to the 74. But there's other probabilistic hurdles that have to be overcome. If you want to build a protein, we know from chemistry that you have to attach the amino acids together with what's called a peptide bond. In nature, peptide bonds occur with about a 1 in 2 frequency. Half the bonds that form between amino acids are peptide bonds, half aren't. But if you get any bonds forming that aren't peptide bonds, you can't form a protein. So to form a protein, 150 amino acids long, you've got a 1 in 2 chance at each site of getting the correct type of linkage. So you got 1 in 2 times 1 in 2 times 1 in 2 times 1 in 2 to the what power? Close to 150. Since we got linkages, we have 149, but call it 150, okay? So in other words, we got another huge exponential problem to overcome. So, and it turns out that 1 in 2 to the 150 is the same number as 10 to the 45th, 1 in 10 to the 45. So now we got 2 incredibly improbable things that we've got to overcome to build a functional protein by chance alone. One more problem. When you're building proteins, amino acids come in 2 flavors. There's a left-handed flavor and a right-handed flavor. They're called optical isomers, not flavors, okay? And the left-handed version is the only kind that can be used in building proteins. You get even one right-handed amino acid in there, and your protein won't fold properly. So you got another probabilistic hurdle to overcome. So you've got a 1 in 2 chance at each site again, out to the 150th power. 2 to the 150th power, again, is 10 to the 45. Oh my goodness. So the odds of building even a short functional protein by chance alone is 74 plus 40. You can remember how you do this in math? You can add the exponents if you're multiplying exponential numbers. Thank you very much. Okay? Wow. Now, can anyone get their mind around a number that big? There's only 10 to the 80th elementary particles in the entire universe. There's only 10 to the 16th seconds since the Big Bang. There's only 10 to the 139th total events since the beginning of the universe. Now you're starting to get the understanding of why people are very skeptical that the chance hypothesis is going to do the job. Now, you may have heard just the opposite. Has anyone ever gotten in a discussion with you about the origin of life and said, hey, it happened by chance? I mean, do you hear that? I mean, this happens to me. I'll be lecturing in hostile university environments, and I'll get done and somebody say, well, but, and they want to argue with me about the probabilities. And I just shut the discussion down because I say, no serious scientist thinks this is the way it happened. It's always going to be more probable that it didn't happen by chance than it did. And with that kind of reasoning, you realize it's time to move on and look at some other options. It's a real simplistic illustration, but you got a card player. His name is Waco Willie. You should immediately be suspicious, okay? And Waco Willie is, he's winning every time. You're playing poker, and every time he's pulling that straight flush, okay? And you say, hey, wait a minute, Waco, you're cheating. What are the odds? And he says, what do you mean, what are the odds? Improbable things happen all the time. You just had 10 hands of cards, and those exact 10 hands of cards were really improbable. What's the fallacy in his reason? What about his 10 yeah? He's always winning, right? His improbable event is performing a function, right? It's accomplishing something. There's an end or a purpose being actualized by that improbable event. Remember our illustration with the lock from a couple of lessons ago? If you've got something highly improbable that's also performs a function, then you're not just dealing with chance. Something else is at work. And that's basically what the scientists have concluded. That if we were just dealing with an improbable event, that'd be one thing. But it's an improbable event which is also critical to the function of life. And that improbable event is the origin of a protein. But let's just say one more thing. All this time we've been talking about how many proteins. You can read the answer off my finger. Okay, all right. We're only talking about one protein. How many proteins does it take to make a single cell? Well, nobody knows exactly, but the estimates are it would take about at least 400, well, between 250 and 400 proteins, the estimates vary, to produce a minimally complex single-celled organism. There are vastly more proteins in the cells in your body. You have lots of different cell types. Do you get a sense that maybe we're taking a lot for granted when we think about, we live in these wonderful bodies, we have all these trillions of cells in our bodies. Every cell in our body is comprised of hundreds of different kinds of proteins that do hundreds of different kinds of jobs. And then we encounter somebody at a dorm bull session and they say, hey, well, life just happened by chance. Well, wait a minute, let's stop and reason this through. Way too improbable, we're dealing with specified information, and if every event in the entire history of the universe was devoted to trying to find even a single protein, there wouldn't be enough time to search all the possibilities. This is not a good hypothesis, okay? So don't get bullied on this one, all right? And because most scientists, I would say that, in fact, I don't know of any scientists who work on the origin of life who think differently. They have been looking for other alternatives, and that's what we want to talk about next. Let's move on now and look at some other ways that people have tried to explain the origin of information. And one of them is the idea of prebiotic natural selection. If you remember Darwin's idea, Darwin didn't just rely on chance, he also brought in the idea of natural selection. And with natural selection, you have organisms that are reproducing, you have new offspring, there's a fight for survival, competition for survival. If the new generation has inherited a trait that aids in the survival, then that's going to be passed on to the next generation. Okay? It will be selected naturally and passed on. Some scientists said, well, since the odds against life arising are so small, why don't we invoke natural selection at the prebiotic level and say that it happened before life arose? And that helped make incredibly improbable things much more probable as desirable variations were selected step by step by step. Anybody see a problem with this? Yeah.
It's not alive yet?
Yeah. It's not alive yet. That is exactly the problem. Okay, natural selection depends upon what's called differential reproduction. One of the organisms that received a trait in the new generation has an advantage over the other organisms who didn't get that trait. But the whole mechanism presupposes that you have organisms that can copy themselves. That copying in actual cells depends upon, interestingly, information-rich DNA and functional proteins. But what are we trying to explain the origin of? Exactly, functional DNA and proteins. So we have what's called in logic the problem of begging the question. Natural selection depends upon self-replication, but self-replication depends upon the existence of sequence-specific DNA and proteins. And when we say sequence-specific, we mean information-rich. All right? So I got a way of explaining what's wrong with this way of thinking, okay? Guy is walking home from work, and he falls into a big hole. So he thinks to himself, and then suddenly he gets an idea. He says, no problem, I'll just go home and get a ladder, and then climb out. So he goes home and he gets a ladder, comes back to the hole, jumps in the hole, and climbs out. Okay, what's the problem? Yeah, how do you get out of the hole? He's begged the question of how he gets out of the hole. Okay, and that's the same logical problem that's beset the idea of prebiotic natural selection. You can't get natural selection going to explain the origin of new information until you already have information. And one of the leading scientists in this area said that theories of prebiotic natural selection have a big problem. They need information, which implies they have to presuppose what they're trying to explain in the first place. All right, now let's look at one other approach to the origin of life, and this tends to be more where the action has been in recent years. and it's the idea of self-organization. This idea was first proposed by a scientist named Dean Kenyon, who wrote a book called Biochemical Predestination. His idea was that there are forces of attraction between the individual parts of the protein or the individual parts of the DNA molecule that would cause them to arrange themselves in a certain way and produce the information that we recognize in those key arrangements. Now, this isn't a totally crazy idea at all. We know there are chemicals that have highly ordered structures that are the result of forces of attraction between the individual parts or elements in those chemicals. Can anyone think of an example of that? Salt. NaCl. Positive charge, negative charge, attraction forms a structure. If you put a lot of the ions in solution, let the water evaporate, you'll get a nice crystal, highly repetitive structure, NaCl, NaCl, NaCl. There were natural forces that are responsible for the arrangements, the forces of attraction. That was Kenyon's idea. He said maybe that's the explanation for the origin of the sequential arrangements in the proteins. Now here's the interesting thing. I first encountered Kenyon at a conference in 1985. I was a young scientist, and I came in off the street to this incredible conference about the origin of life. And Kenyon was a very well-known person because he'd written this book, Biochemical Predestination. At the conference, he was explaining why he had come to reject his own ideas about the origin of life, why he thought his own theory was completely wrong. Kenyon had come to realize that the critical question wasn't the origin of proteins. It was the origin of the information in DNA. And he realized that there was no way that you could have forces of self-organization explain the arrangement of those characters that make up the digital code. And let me explain why. Let me give you an illustration that I thought of when I was first few years of teaching. My kids were little, and they were always spelling messages on the chalkboard with these magnetic letters. And so I've got a message here. Can everyone read it? Self-organization, okay? Notice that you have a force of attraction that explains why the S here attaches to the chalkboard. It's a magnetic force, right? But are there any forces that explain the arrangement of the letters in this message? Okay? You're shaking your heads. No, but we can demonstrate that, can't we? Because we can simply rearrange these and create some gibberish very quickly, and we've got the same physics and chemistry, but now we don't have any information. Okay? So the same thing, it turns out, is true of the information in the DNA molecule. Can you guys see that in the DNA, you've got the message-bearing axis is the A's, G's, and T's along this direction, okay? The sugars and the phosphates here are the backbone. They don't contain the information, they just store it. That's the place where the information is attached. The information is here, okay, in this axis, all right? You've got no forces of attraction between the letters, and moreover, you have the exact same kind of force of attraction between the letters and the backbone of the molecule to which the message is attached. So this is the medium, and this is the message. But the message is not governed by any force of attraction. This bond will receive any one of those four characters, A, C, G's, and T's. Just like on the magnetic chalkboard, I can stick this O anywhere I want. Okay? So the forces of attraction do not govern the sequencing. Does everyone see that? All right? Not here in this system, not in the DNA. So what you're dealing with is a true message system, but it's not governed by physics and chemistry. Now, there's a famous chemist who was a friend of Einstein named Michael Polanyi, who was the first person to actually recognize this. And he used an analogy also to get this across. He says, as the arrangement on a printed page is extraneous to the chemistry of the printed page, so is the base sequence in a DNA molecule extraneous to the chemical forces at work in the DNA molecule. When I had the message back on the board, where did the message come from? Was physics? Me. What? Me. Am I part of nature or something? Am I a physical, chemical? You're absolutely right. Came from a mind, didn't it? Came from an intelligent source. This is what Polanyi's saying. It's the information is extraneous. It's outside physics and chemistry. I think he was hinting at the idea that it must have come from design. He didn't come right out and say that. Okay, so what do we conclude from all this? Well, I think we conclude that undirected processes do not produce the information you need to produce the first life. We've looked at three different types of undirected processes. Chance alone, We've looked at necessity, the self-organizational approach, and then we've looked at a way of combining the two. And this is what actually a number of scientists are increasingly coming to see, is that there is no naturalistic explanation for the origin of the information that you need to build the first life. Undirected processes don't get the job done. Well, if there's no undirected mechanism or cause that can produce the origin of the information you need to explain the origin of that digital code in DNA, maybe we're looking at something that appears designed because it really is designed. And so in the next lecture, we're going to move from just looking at these undirected processes to considering an alternative approach. The idea that the design that we see in the digital code may be pointing to an actual intelligence.
In this Old West cemetery are buried the miners, the gunfighters, the pastors, and the prostitutes. This is a tomb for a 5.5-month-old baby. Now, the odds of each one of us ending up in a place like this?
Some big numbers of probability thrown out in there, and I don't know about you, but have you learned anything about amino acids and proteins and how all that has to be arranged in order to get life? The incredible odds of this just happening, if you understood what he was saying, is so astronomical that we can't even wrap our heads around that, which is incredible. In fact, he makes a statement, and it's the basis for my faith, I'm here to tell you, is it's far more probable that God created all of this than it is to believe it just happened. I mean, that is at the core of my faith when it comes to looking at nature. I cannot see it just happen. There's too much, it's too complex and it works too well. But did you understand about his comparison to an alphabet and how all of that works? So if you look at an amino acid like a letter in an alphabet, you can throw any kind of pile of amino acids up there that you want, but it takes an intelligent source to arrange those amino acids into what in our language would be a word that means something. And we're talking about such huge volumes of stuff here. Not only are we arranging letters into functional words, we're arranging functional words into functional sentences and making information at a novel-sized level. And the probability of that just happening is just incredible. I don't know how you get around the idea of there not being an intelligent creator behind all of it. And this is in one cell. And you're made up of trillions of those cells. In you and in me, in every animal you see, in every plant you see, that information is embedded in every one of them. It makes them, they're very unique individuals. I find this stuff very fascinating, and I got to tell you, it's over my head in some ways, and in other ways there's enough there to, once again, to make me believe that they're the most probable answer to our existence isn't by chance. It's by design and from God, just like the Bible tells us. Questions or comments? All right, let's share a prayer together and we'll be dismissed. Our Heavenly Father, Lord, we are indeed wonderfully made. As your servant David was so observant way back when. And Lord, I think to myself what David knew about how we're created and, Lord, what we know today, and I can't help but think that we're just starting to scratch the surface of the wisdom behind your creation. Lord, I want to thank you for giving us evidence that builds faith, evidence that shows us you are indeed the one true and living God. Lord, thanks for blessing our time together today. And Lord, thanks for loving and caring for each one of us as you do. It's in Jesus' name we pray. Amen.